Hi there, and welcome to the lecture video for section 3.1 on the topic of determinants. Here in this section, we are going to define this special number called a determinant of a matrix. And we're going to see a little bit about how to compute these things and talk very briefly about what they're used for. We will get more into the discussion of what they're used for later on. For now, we want to stick with the basics of what are these things and how do we compute them? Given a matrix, how do I find its determinant? So let's start here. Every square matrix has a number called its determinant that's associated with it. And it turns out this determinant is useful in theoretical results, often in developing proofs. And one reason that is because now, as we'll see, once we have a determinant, we can actually write a formula for, I have a typo here, not a matrix itself, but a matrix inverse. In terms of the determinant of the matrix. And so this is a nice result. Finally, we will have a formula for the inverse, not just some sort of process for finding it, right? Remember, we've usually used row reduction to find inverse matrices, but we never had a good way of writing down, given matrix A, what does the matrix A inverse equal in terms of A's components? Well, with the determinant, we will be able to do that finally. So that's one reason it's useful for proofs and theoretical results. But we are going to focus on mainly just how to compute these things in this video. So let's start out with a simple definition of a determinant of a 2x2 matrix A. We are going to start out with just these 2x2 cases, and we will then extend this to be able to handle larger dimension square matrices. So the determinant of a 2x2 matrix A, we denote that this way with what look like absolute value bars around a matrix. That means determinant of A. And it's given by, if matrix A has components A11, A12, A21, A22, that's how we labeled the elements of A, then the determinant of that matrix is A11 times A22 minus A12 times A21. So if you notice, that is the product of the main diagonal elements, A11 times A22, minus the product of the off diagonal elements, A12 times A21. So you can think of this as being the difference of the products of the two diagonals, the main diagonal minus the off diagonal product. Other notation to represent the same quantity, instead of using these bars here, you might see determinant of A just written det of A. And that's certainly perfectly acceptable. You can write either of those freely. In fact, we write det of A. That is the exact syntax you use to compute a determinant in MATLAB or Octave. If you want to do that, you just enter your matrix, A equals, enter in that matrix. Then once you've got the matrix stored, you can write det of A, and entering after that will give you the determinant of your matrix. A quick example here, just to make sure we see how to use this formula. If our matrix A is 3, 2, 1, 4, then the determinant of A should be, maybe you can pause the video briefly and write this down, shouldn't take more than a minute. 3 times 4, that's the main diagonal product, minus 2 times 1, that's the off diagonal product. So that's 12 minus 2 is 10. Now what that 10 represents is still yet to be discovered in this course. We'll talk about that more. How to use that number, we'll figure out more later. But for the sake of just computing a determinant, it's as simple as that for a 2x2. Main diagonal product minus off diagonal product. So let's now talk about how do we define determinants of matrices that are larger than 2x2, say a 3x3 or a 4x4 matrix. How do we work those out? We can't just apply this formula. It certainly doesn't apply when we have more elements over here. So what will we do? Well, we define a few other objects first to help us define these bigger determinants of bigger matrices. First, we define the minor of a given element of a matrix. So given a matrix A with elements kind of labeled this way, A11, A12, A13, and so on across the first row, right? Where your IJ index is telling you the row I and column J that your element lives in. So if you have a matrix labeled that way, then the ij element, the element in the ith row, jth column of A, has a number associated with it called the minor of that element. It's denoted mij to go with aij. So this minor of the element aij is denoted mij. And it equals the determinant of the matrix remaining after you remove the ith row and jth column of A. So whatever element in this matrix I want the minor for, I remove that row and that column from my matrix, and that condenses down to a smaller matrix that I would compute a determinant of. Right? That determinant is called the minor that goes with the ijth element of the matrix. And we'll see this in an example. So if the wording isn't so clear, I think it'll be very clear after we see an example. So we define the minor that way. We go one step further. I should underline this too, something else we're defining. We then define the cofactor of that same element aij. Instead of, right, the minor, we denote mij, but the cofactor for aij, we denote cij. And all it is this minor we already established, mij, but with -1 to the I plus j power attached to it. Which notice, since it's -1 to some integer power, I, the row you're in, plus j, the column you're in, this is just -1 to some integer power here. This number will always be positive or -1. We just have to figure out which it is. Right, whether it's positive or negative depends on the sum I plus j, which depends on the row and column that we want the cofactor for. Okay, so noting what I mentioned here, the minor itself, mij, and the cofactor, cij, differ at most by a sign. This weird stuff out front is either a +1 or at worst a -1, and it flips the sign of the minor. And so you might be saying, why in the world are we defining these very strange things this way? Well, let's see why we're doing this. Oops. In an example. Given matrix A here, let's compute the minor and cofactor of A21. All right, so let's figure out the minor first. Let's figure out M21. Remember, if I look at this element, A21, in my matrix, that's second row, first column. So we're really talking about this 1 that sits here that I just circled. That's A21. So the minor, M21, that goes with that entry is the determinant of the matrix that remains when I get rid of the row and column that A was in, right? Or that A21 was in. So second row, first column, I'll delete those. I deleted the second row and the first column. And look at all the entries that remain. The 2 and the 3 remain. The 2 and the 1 remain. So that tells us this is the 2x2 determinant we need to take in order to find the minor that goes with A21. So this determinant's very easy though. It's just 2 times 1, main diagonal product, minus 3 times 2, off diagonal product, which is -4. So M21 is -4. That's your minor. For entry A21. Now, if I want to figure out what the cofactor for A21 is, we call it C21. Remember, that's just -1 to the I plus j power times M21, which is -1. In this case, my I is 2, my j is 3, my j is 1, sorry, the sum is 3. So I plus j up here. It's 2 plus 1. This is a j, not a y. So that's -1 to the 3 times M21 was -4. This equals -1, -4, makes +4. So the C21 cofactor, the cofactor for the entry of the matrix in the second row, first column, is 4. And that's it. Okay. Now, how does that help us compute determinants of matrices larger than 2 by 2? Well, really, we define the rest of the larger matrix determinants, we define them in terms of these minors and cofactors, really the cofactors. So let's look at our definition here. The definition we're going to use is that the determinant of an n by n square matrix is the sum of the products, we're adding up a bunch of individual products, of the elements of the first row with their corresponding cofactors. So A11 times C11. A21 times C, let's not try to say it in words, right? It's already complicated. It will be very clear with an example though. All we're saying here is that just like I found the cofactor that went with A21, that entry that was in the second row, first column, we're gonna say the determinant of this square matrix can be computed by finding each of the entries in the first row, find each of their cofactors, multiply the entry by its cofactor, and add the results across every one of these entries in the first row. That's complicated to say in words. It's complicated to write down in a nice, clear way. But I think showing it in an example makes it very clear what we're doing. So let's see this example here. A is this matrix 1, 2, 3, 1, negative 1, 1, 0, 2, 1. Same matrix I used up here. And we're asked to find the determinant of A. Notice all this is saying the determinant is the sum of the products, so sums of the products of the elements in the first row of A, so that's the 1, the 2, and the 3, times their corresponding cofactors. Right? This is A11, so we multiply it by C11. This is A12, so we multiply by C12. This is A13, so we multiply that guy by C13. And we just add it up for every element across the first row. Multiply the element by its cofactor, add that for every element across the first row. That's how we're going to define our determinant. And we'll see here it becomes pretty simple. A11, right? We said that's first row, first column. That's a 1. Times C11. Well, C11 has this negative 1 factor raised to the ij, the I plus j, which is 1 plus 1, times M11. Right, that's our formula for the cofactor, C11. And we'll just write that out. We'll come back to that in the next line of work. A12, that's this guy, times C12, which again is just negative 1 to the I plus j, so 1 plus 2, times M12. All the way down the row, the last entry in the first row, A13 is 3, multiplied by C13, which is just negative 1 to the I plus j, 1 plus 3 power, multiplied on M13. Okay, so I'm just clearing this out one step at a time. You'll see that after you get the hang of this, you can probably skip at least this first step I'm not writing out in full detail. I'm just trying to make it very clear how we're using that definition of the determinant. So then I go back through and I want to compute these minors, but the first minor here, I've got really negative 1 to the 2 power, so that's positive 1. Times this first minor is a determinant all on its own, right? M11 is the 2 by 2 determinant we are left with if we get rid of the 1, 1 row and column, row 1, column 1. So we'd be left with this little 2 by 2 matrix that we're taking a determinant of to get the M11 minor. Now let's just move on to the next. Here we have 2 times negative 1 to the 3 is negative 1, so I'll just make this a negative 2 overall. M12 says erase the first row, second column. Take the 2 by 2 determinant of what remains, right? First row, first column removed. 2 by 2 determinant of what remains, 1, 1, 0, 1. Next entry here, we have 3 times negative 1 to the 4th is positive 1, so that's just a 3. M13 What is M13? Get rid of the first row, that's the 1 in the index. Third column, that's the 3 in the index. And look at the 2 by 2 matrix you have left. You want that guy's determinant. So let's put all this together. 1 times, this determinant is -1 minus 2. Minus 2 times 1 minus 0 plus 3 times, computing this last 3 by 3 determinant, I get 2. So add it all up. -3 minus 2 plus 6 is 1. The determinant of this 3 by 3 matrix up here is 1. And so you might notice that, and if you've worked with determinants before, you will certainly notice that probably you don't need to write this second step. Really, all you want to do is memorize the pattern that these signs take in the cofactors. Let me go back to the cofactors. The signs here follow a very certain pattern, right? We're saying that depending on the entry ij that you look at and want the cofactor for, so depending on what row and column you're at, this sign will change either from a positive to a negative, or it could be either of those. But it all depends on what I is and what j is, what row and column you're in. So I've written this down at the bottom of the next page. Let's notice the pattern for those signs on the cofactors, that -1 to the I plus j. If I'm in the first row, first column, that's 1 plus 1, first row, first column, 1, 1. Add those up, you get 2. -1 to the 2 is positive, so I put a positive here. And if you do that, for example, in the next entry, first row, so row 1, second column, so column 2, add those together, you have a power of 3, which makes a negative. That's a power on a 1, so on a -1. So you get a negative here. And if you continue doing this for every ij possible in a matrix, you just get this kind of checkerboard pattern. Plus, minus, all the way down. Next row picks up, continuing this pattern, minus, plus. Right? It works out very easy in terms of the signs that will be attached to each minor. So for example, up here, when we went across the first row here, we could have just said, take entry 1, and then, right, that's what we had here. That's our 1 from the A11. And then just look at the determinant of what's left when we cross out the row and column that it lives in. That's our determinant here. All we're going to do, though, is say that since we were in the first entry here, we know that, according to our plus-minus pattern, gets a plus. So we don't need an extra negative outside. But when we move on to the next entry, the 2 here, according to that plus-minus pattern, plus, minus, plus, this guy always gets an extra negative. So I'll put a negative out front, followed by just the actual entry that was there, this 2, followed by the 2 by 2 determinant that remains when we cross out the row and column that that entry lives in. So the 1, 0, 1, 0, and 1, 1. So probably, rather than computing this C value, the actual cofactors, probably you're just computing minors and just memorizing the pattern for how the signs go. You'll get this down pretty quickly if you haven't played with this before. If you have played with determinants before and computed these before, probably you already think in these terms of this checkerboard pattern. Okay, so let's see another theorem. We were very specific when we defined this determinant to say that we had to expand in these cofactors using the entries in the first row. It turns out that really this works if you use any specific row or any specific column of your matrix A. So long as you add up the entries in that, the product of the entries in that row or column with their corresponding cofactors, it doesn't matter what row or column you use, you will get the same determinant. Pretty amazing fact here. For example, you could expand in any of the ith rows, I equals 1 through n, or you could expand in any of the j columns, j equals 1 through n. And the form of the determinant takes this sort of, it looks something like this when we write it all out in our notation. Right, just like for the 3 by 3 case, expanding in the first row gave us this. That's kind of like replacing the n with 3 since we had 3 by 3 and the I with 1 since we used the first row. Okay. And again, notice that you still can only worry about you can choose to only worry about the minors and just get the signs correct for the cofactors based on this checkerboard pattern, applying pluses and minuses to the minors according to this pattern. So let's see, in all its glory, computing one of these determinants. Let's find the determinant of A for this big matrix A. And I'm going to choose here, as I've written, to expand in column 1. Notice that has the most zeros. So as I add up the products of the entries in this column with their corresponding cofactors, the entries themselves are going to cancel out the cofactors for these 3 entries. So it'll save a lot of work. So all I'm going to have to do here is expanding in column 1, I get 1 times the 2 by 2, in this case 3 by 3 determinant that remains when I cross out the first row and first column. So I get -2, 2, 0, 3, -10, 1, 2, -1, and 0. That was just from this guy. The next entry in that first column is the 0 here. So I'll say, remember the plus minus pattern, plus minus, plus minus. That next entry gets a minus with it. And if we didn't have a 0 there, we'd care a lot more about what comes next. We do have 0, so it really will cancel out whatever we're about to multiply it on. But for clarity, I do want to go ahead and write out this determinant that would be attached to. Cross out the row and column that that 0 lived in. What do we have left? We have this. So I'm going to fill out the rest of this line of work. Same way. I'll say plus 0. Checkerboard pattern. Plus 0 for the next one. Cross out that row and column. That's the 3 by 3 determinant we have left. And finally, the last one would be a minus 0 times. Cross out the row and column. And we see the 3 by 3 determinant that remains. So what do we have here? Now we have this determinant problem, a 4 by 4 determinant, broken down to just resulting in really 4 3 by 3 determinants. We got lucky in this case. We expanded in a column with a lot of zeros, meaning this guy's going to disappear. Right? We're multiplying it by 0. This guy will as well, and this guy will as well. So we really, luckily, only are left with this stuff. The 1 out front isn't changing any of this stuff, so I'm just going to copy down this remaining determinant. And check out this. We have another opportunity to practice computing determinants here. I would recommend at this point maybe pause the video, see if you can finish this one from here. I'm going to go ahead and proceed now, so hopefully you've already paused if you want to try it on your own. I'm going to expand in the 3rd row this time, 3rd column this time. Notice I'm choosing that because that is going to give me the most zeros possible, which is going to simplify my work as much as possible. So remembering this checkerboard pattern, starting with this 0 here, we get a positive 0 times the 2 by 2 determinant that remains when we cross out the row and the column that that guy lived in. So just the 3, -10, 2, -1. Now the next entry down, we have positive here. The next one will be a minus attached to that 1. And cross out the row and column that this 1 lives in. What's going to remain? -2, 2, 2, -1. Finally, down to the end, plus, minus, plus again for this guy. 0 times -2, 2, 3, -10. Okay. So let's see what we get from here. Again, utilizing all these zeros makes it kind of easy. These guys fall out. We just have -1 times -1 times -2 is 2. -2 times 2 is 4. So we get +2. So at the end of the day, the determinant of A equals 2. Okay, kind of a complicated problem there, right? So one last little thing to end with in this video is maybe a shortcut or a trick for computing some of these determinants. Notice we already said that in the case of a 2x2 matrix, A11, A12, A21, A22, we could multiply along the main diagonal and subtract the product along the off diagonal. A11, A22 minus A12, A21. So if we kind of think about the pattern there, we took all the top left to bottom right diagonal entries, multiplied those and gave them a positive value, and took all the off diagonal, so top right to bottom left diagonal, multiplied those and gave them a negative, and just strung them all together. And it turns out if we view it with that pattern, a 3x3 determinant fits a very similar pattern. It's just we have a little bit of trouble here. So let's see how we can follow a similar pattern. It turns out if you take a 3x3 matrix like this and copy again the first two columns out at the end, so the first column I've recopied here, and the second column I've recopied here, just like we're cycling through these columns, then it turns out you can go through this same sort of thinking. Take the first diagonal that goes from top left to bottom right, that'd be your main diagonal, multiply those three together with positive signs, just like we did when we were descending to the right this way. We gave those a positive. Multiply all these together with a positive, but now do the same for your next little rightward descending diagonal. Start here, then A23, then A31, multiply those and give those a positive. And A13, A21, A32, multiply all of those and give it a positive, right? That's like multiplying, taking all the rightward descending diagonals and multiplying them and taking each with a positive, and taking all the, I guess, leftward descending diagonals, A13, A22, A31, A11, A23, A32, A12, A21, A33. Those are our leftward descending diagonals here, and attach a negative after you multiply those corresponding entries. With that sort of pattern, which is exactly the same as what we really did up here, you get an exact expression for the determinant without having to go through all the minors and cofactors. So let's see what I'm saying. A11, A22, A33, that's here with a positive. A12, A23, A31, that's here with a positive. A13, A21, A32, that's here with a positive. That's all your rightward descending diagonals multiplied and given a positive. All your leftward descending would be what come next with negatives. A13, A22, A31 with a negative, that's here. A11, A23, A32, that's here with a negative. A12, A21, A33, that's out here with a negative. So sometimes this is pretty useful. I mean, if I just have a matrix of actual numbers, this is very nice and easy, typically, to get a computation done in an easy way. If I was dealing with some unknowns in this matrix, maybe this gets a little complicated. Maybe you'd rather compute with minor expansion and cofactors. That'd be just fine. But it's nice to know there is sort of a pattern you can pick up on from 2 to 3, 2x2 to 3x3 determinants. The last thing to mention though is that unfortunately there aren't any good tricks like this for n greater than 3. So for example, this 4x4 up here, we were kind of stuck doing it the way that we did do it up here. There wasn't a nice pattern you could follow like we followed for like we wrote down for the 2x2 or 3x3 cases. So bigger than 3x3, you're stuck expanding cofactors. Okay, that is it for this section. We'll see more about determinants in the next video. Thanks for your attention.